Hey everyone, welcome. Today we'll be looking at an example of Dijkstara algorithm. So the question for today, an example for today is implement Dijkstara algorithm to find the shortest path between two cities and also calculate the minimum cost. So what is a Dijkstra algorithm? So Dijkstra algorithm is basically used to find the shortest path between 2 points in a graph. So that's what basically Dijkstra algorithm is. So how do you go about solving this problem? So first things first, hashtag include iostream. You guys know this. Hashtag include iostream for input and output header files, and we are going to include vector header files too, because we will be dealing with vectors, dynamic arrays in this, and we will be including strings too, because we will be giving names to cities, and we also need unordered maps. So what is an unordered map? Hashtag include unordered map. So what is an unordered map? So unordered map is something which is you can visualize it like a container. Each element in that container will have a key and value pair. Alright. The value can be accessed by using the key. So imagine it as a container, and each element inside the container can have two parts, key and values. It is just like a vector, but it has two parts, key and value. And the other things which you can include is hashtag include um, limits. Yeah, you can include them, as this is basically used for including the contents of the limits header file. Now, why do we need this limits header file? The limits is used to get information about a character we are entering. Like, let's say you're entering a number, you want to know whether the number is signed or not. So it will help you to tell whether the number is positive or negative. So that's kind of why we use limits. And we're also going to include stack data structure, and also you're going to also include queue. So I think this is it, and yeah, using namespace std you can. So we have included our respective very useful header files. So now we will have to write the function for Dijkstra's. So I'm going to write void Dijkstra and then I'm going to make an unordered map in which I'm going to give two things, string, and within that I'm going to define another unordered map which has two parts, string and int. Alright, and I'm going to close it, and I'm going to close it again, and then I'm going to name the unordered map, and I'm going to name the unordered map as graph. So graph, and I'm going to name another string called start, and I'm going to name another string called end. So what I've basically done in this, that we have declared a function called Dijkstra, and we have given three parameters to this function. The first parameter is used to create an unordered map called graph, and a graph has nodes, right? These nodes have a name, and those are all strings. So that is what we mean by this. But what about the others? In a graph there are edges and distances, right? So if you actually see from a node, each and every edge from a node is actually uh, an unordered map in itself, because it has the edge name and it has the edge value. So that is why we are implementing an unordered map inside an unordered map. So this denotes the name of that node present in the graph, and this is the name of the distance, name of the edge, and the integer denotes the distance, the edge distance. So that is why in a graph we have two unordered maps, one within one, and this is const string, and we are maintaining a constant string, which is the start is the start vertex, the point from which we want to start, and the end, which I have written, is the one in which we are going to end, the destination. So now we can start writing the function. The first things, we can use a priority queue to implement graphs. So let's see how it's done. Priority queue, and I'm going to give pair. Remember, priority queue also has a key value pair. So pair int comma string I'm going to give, and then I'm going to give vector pair int comma string. These are all present inside the priority queue. The vector, the name of the priority queue, everything is present. So int comma string, and I'm also going to get another thing called greater, which is a pair, or which is also a pair, and that is present inside a priority queue. So, and I'm going to close this, and I am going to and I'm going to reference it, and I'm going to end this. So what have I done here? So I've declared a priority queue, PQ. This is priority queue. I have named the priority queue PQ, and uh, each priority queue, we know each priority queue element has a pair of string and an integer. The integer is used to represent the weights in graph, and the string is used to represent the names of the nodes. Okay, that is why we use a priority queue. We have to denote the name, or we have to denote the name and also the edge distance. So we are using a priority queue to store it. So priority queue vector is the container in which we have used the vector here, right? Priority queue vector. It is a container in which the elements are stored, all our edge distance and things. We need something to store those, right? So we have a vector, priority queue vector, and in a priority queue, there has to be a condition for the order of priority, because what is a priority queue? Based on higher priority, elements are accessed first, so that is what is priority queue. But we need to give a condition, whether if higher value element should be given higher priority or lower value element should be given lower priority. But in this case I have given greater, which means that it is a min heap. Greater here denotes it is a min heap. And what is a min heap? Lower values are given higher priority. So that is the meaning of this. So that is what is in the explained in the above line. But now I'm going to call the unordered map, and I am going to define a string, and in string and int, and I'm going to name that unordered map as distance. So what I have done here is that the distance container, that unordered map, contains the name of the node from which edge is and the value of the weights. And I'm going to create another unordered map in which I'm going to store string and another string. and I'm going to name this previous. And what I've done in this line is that I have created a container previous, and it stores the name of the current node and the previous node. So that is why two strings. I've used two strings in this unordered map. And now what I can do is that I have to initialize every single node with infinity at first. That is what is the Dijkstara algorithm. First, we need to give the maximum value for we don't know anything. So for that, I'm going to use for const auto and entry, which is in the graph. I'm going to say that distance of entry dot first is equal to numeric limits, and it is an integer, and I'm going to set it to max. So what have I done here? So in the above for const auto is used to automatically deduce the type of elements we are using and what we are dealing with basically. So the auto keyword directly, it knows what you're using, whether it is a string or integer. So, and the entry denotes each element which we are going to store. The entry is the key value pair or the paired elements, and these are for a graph. So that is why we have used colon and graph. And what do we mean by distance of entry dot first? Here, the entry dot first denotes the string of nodes or name of nodes we are assigning distance on node or map to. All right, because entry is the element and entry dot first is the string contained in that element. We have an element and it has two things, integer and string. We are specifically accessing the string of that element, so that is why I used entry dot first is equals to numeric limits. What is numeric limits? This is what we got from the limits folder. So this is why we use limits. So numeric limits is the package which is the one which is obtained from the limits header file, and we are going to set the limits to maximum value possible. So numeric limits int, the integer should be set to max. Max is something which is undefined, a very high value. So that is why we use this line. And after that, what we are going to do is that we are going to set the distance of start equals 0. Now we set the first start index to be 0. Now we need to push this into the priority queue. Now for that I'm going to use pq.push of 0 comma start. Now because pq is a key value pair, we need an integer and a string, so that is why 0 comma start. Now I've done this, but now what should we do now? So we need now from now onwards the main loop of Dijkstara starts. So I'm going to say while this priority queue is not empty, I'm going to define a distance called int current distance equals pq dot top of dot first. What am I doing? So in an pq there is integer and string stored. So in order to get the current distance which I want, I'm going to look at the top of the priority queue, and in that first, so I want to look at the first top of the priority queue, and I'm going to access the integer. And in the second, I'm going to define another string called current node, and I'm going to look at the second top, pq.top of dot second. So this will access this string which is present in that element. This one will access the first, then this one will access the second, and then we are going to, once we access this, we don't need that memory, we are gonna pop it off. So I'm gonna say pq.pop off. I'm gonna remove that element. Now the condition, if current distance which I have declared is greater than the distance already marked with current node, then I'm going to say that don't do anything, just continue. You don't have to process anything. If this condition is satisfied, if what we saw above the priority queue is greater than the distance already there, you don't have to process anything. You just have to leave, because that's what we want the least distance there, and if this is least, then it should be like that. So we don't want to perform any operations, just continue. So yeah, now this is the above is the main loop. Now we will look at something called relaxation step. Now in the relaxation step, we want to consider the neighbors of the node of a particular node to particular node. So how do you do that? Particular, yeah. So, and I'm going to define a for loop again, for const auto, and I'm going to define neighbor, and I'm going to say graph dot at of current node. Now what is this? So what I have done is that we are assigning a name to the neighbor. All right. uh, so I've used a neighbor, and at the current node we want, there is at a particular node called current node in the graph, I want to calculate the neighbors. I want to see who the neighbors are. I want to calculate the distances, everything. So that is why I've written graph dot at of current node, at that current node. So what I'm going to do is that I'm going to define a string called next node. I'm going to define a string called next node, and I'm going to say it is neighbor dot first, which is saying that the string of the next node is the first uh, first block. All right. Yeah, and the int next node, and I'm going to say the int weight equals neighbor dot second, and I'm going to say int distance 1, because I've already used distance 1 is equal to current distance plus weight. So what I've done is that in the first line, string next node equals neighbor dot first, I have assigned the neighbor element string as next node. The string is the first part of the neighbor, and then what I've done is that the int weight, I've declared a weight, and I'm assigning the weight of the neighbor node as the integer of the neighbor node. Alright, whatever that neighbor node has already, I'm going to assign that number as the weight of the uh, current node. Okay, weight of the neighbor node, sorry. And I'm gonna declare a variable called distance 1, which is the sum of current distance of the current node, how much ever distance that current node we are interested in has traveled, and the weight of the neighbor node to which we want to travel. So that is why I've summed up current distance, whatever we have traveled, plus the way that amount of distance we want to travel. So that is why current distance plus weight. So now I'm going to write an if loop, if statement. If distance 1 is less than distance, then we are going to tell that distance of next node, then distance of next node equals to distance 1. I'm gonna tell this. Now what have I done here? Distance, I will be telling it distance of next node equals distance 1. And now what I'm going to do is that I'm going to tell the previous of next node. I'm going to tell the previous of the next node is equal to current node. I'm going to tell this like this. Now I want to push this pq dot push off pq dot push off. I'm going to push the next node and the current node. Sorry, the distance and the current node. So I'm going to push distance 1 and the next node inside the priority queue. So yeah, if the distance 1 we have calculated, current distance plus weight is equal to distance 1. If that is less than the distance of the next node, which is the neighbor node, next node, then distance of next node equal to distance 1. We are assigning the distance of next node as the distance 1 because it is lesser. And then the previous of the next node is equal to current node. We are retaining the copy from which parent it has been gotten from, and we are maintaining it in a priority queue. So this is what we are doing. So this is the main, we have finished the Dijkstara. Now we are going to print the shortest path. How do you print that? For that, we are going to implement something which is familiar to you guys, stack. We are going to implement a stack, and how are we going to do that? We will implement a stack by which is a string which only has strings, and I'm going to name the stack as path, and I'm going to set the current node string to the end node. Alright, now while current node is dot empty, or if it's not empty, while current node is not empty, what I'm going to do is that I'm going to push this current node inside the path, which is the stack. And now I'm going to tell that current node is equal to previous node. I'm going to tell the current node is equal to previous node. Sorry, previous of current, sorry, not previous node, current node. Previous of current node. Now, what I'm going to do next is that I have to print the stack elements in order, right? So I've defined the stack and how it works. Now I have to print the stack elements. How can we do that? So for that, I'm going to write cout the shortest path is, I'm going to tell, and I'm going to inline here, and I'm going to tell that while the path, well, the stack, which is the path, is not empty, I'm going to tell that cout, I'm going to print the path dot top of. I'm going to print the top of the stack. Stack is based on last in first out order, right? So the last element gone in will be printed out first. So that is going to be printed out, and cout path dot top of. Now we have got the element, so we don't need that element. We are removing the memory. So we path dot pop off. Sorry, path dot pop off. We are going to do it. We are removing the element now. So I'll write comment removing the top element. Now what I'm going to do now is that I'm going to write an if statement. If the path dot top of, if the is not empty, then I'm going to tell that you can print an arrow mark, which is basically for designing. And what I'm going to do next is that I'm going to end the loop, and after that I will finally write cout the minimum cost. We need to find the minimum cost too, right? The minimum cost is, I'm going to give a space here. The minimum cost is the distance, which is the final distance of the end vertex we want, right? And I'm going to finally end it. So yeah, now we are done with everything. This is the minimum cost calculation. Now I'm going to write the main loop in main of. Then I'm going to define the graph, right? And we have to define the points present in the graph, right? Unordered map string comma unordered map string comma int graph equals to, I'm going to tell that so yeah, I've added some cities here. Similarly, you have to basically give the start vertex, start string, and then from which to which place you want to go: Los Angeles, Chicago, Miami, and so on and so forth. Now then what you have to do is that you have to give the start city, right? So I'm gonna write string start city and end city. I'm gonna define two cities, and then I'm going to give I'm going to give cout enter the starting city. Alright, and I'm going to tell that inline, and I'm going to use getLine. Alright, so now I'm going to give getLine of scene comma start city. This means I'm just getting the scene, what start city you want. Then you have to do the same thing for the ending city. Enter ending city. Scene. Sorry. Yeah, I'll use getLine itself. get line cn comma and city, because that is more, looking good. And then I will write, I'm going to call the extras function next, the extra graph comma start city which you want, and then end city, and then finally I'm going to end with 0, so return 0. So this is the function. Let's check if this is running. So yeah, there are no errors right now. And yeah, so this is the for loops. This is the main thing you'll be using. So so yeah, so yeah, I think our code is not having any errors. So let's check it again. So yeah, and so now we can check for any city. Let's say from we want to go from New York, and I want to go to Miami. So yeah, we have got the shortest path. Yeah. So if I want to order this in a little bit more correct way, what I have to do is that uh, I have to take this out. Now let's try again. Now let me do the same thing, and right, yeah, exactly. So the shortest path from New York to Miami is New York, Chicago, Miami, and the minimum cost is to go from start to end is 2,200. Exact path. So this was Dijkstra's algorithm to find the shortest path between two cities and also calculate the minimum cost.